Hi, I'm Miss Byrne, and this is my quick video on Unit 7 Oscillations from AP Physics 1. So what we're studying in this unit is simple harmonic motion. So this is motion where there's a force that's trying to push an object back to its equilibrium position. So for this mass on the spring here, it's in equilibrium when the spring force balances with the force of gravity. And then I can displace it from equilibrium and the spring force will act to pull it back up. And then when it's compressed, gravity acts to pull it back down, or if it's a compressed spring, the spring force would act to push it back down. So we'll look at vertical masses on a spring, horizontal masses on a spring on a frictionless surface, and pendula in this unit. So a pendulum also is oscillating in what's called simple harmonic motion. We're also going to dig into the position versus time, velocity versus time, and acceleration versus time graphs when this force is constantly changing. So this is no longer the case of a constant force. We're thinking about changing forces, and that's what's restoring the system, or trying to restore the system back to equilibrium. So the definition of simple harmonic motion is repetitive motion which occurs when a restoring force is trying to push a system back to its equilibrium position. And the system goes through cycles or oscillations, and there's some vocabulary that we'll go through to explain those. Turns out waves like sound waves and light waves and atoms vibrating in molecules can also be modeled by using ideal springs or thinking about cycles, oscillations, and simple harmonic motion. So for a pendulum, we've got a little vocabulary. We would have a massless rod or a massless string if we're considering a AP question on a pendulum that would have the majority of the mass at its bob or at the very end. And then it would pivot at a pivot point here where the equilibrium position is when it's just at rest, straight down. But then if we displace this massive bob, the component of gravity that's pointing parallel, so I guess it would be this way because my camera slipped. So this way is pushing the bob back toward its equilibrium position. Then it's moving, so it's going to keep going. It's going to stop at the same amplitude that it was displaced to start, ideally, if we ignore friction and air resistance. And it's just going to keep going back and forth and back and forth and back and forth. So with a pendulum, we're actually going to think about amplitude as an angle, a displacement from the equilibrium position. But with the mass on a spring, we'll think of its amplitude as the actual number of meters that it's displaced from its equilibrium position. So a few more pieces of vocabulary. We've got period, which is the time it takes to complete one cycle. So if I displace this mass and I pulled it down, so the time it takes for it to go back down to that initial position. And then the inverse of period is frequency, and frequency is just the number of cycles in a second. So while period is the time per cycle, frequency is cycles per second. So the unit would be 1 divided by seconds, or this is called a hertz after a scientist named Hertz. We can also think about how far through the cycle a mass has gone in terms of phase or just in terms of time. We'll often see time as our x-axis, but how far through a cycle something has gone, we can think of with the symbol phi or phi or theta, saying, where I started it was a 0 degree position, and then at the maximum displacement upward is 180 degrees, and then when it goes back to its initial position, it's at 360 degrees. And then amplitude is the maximum position from equilibrium, and we talked a little bit about that before. These equations in the boxes, green boxes, are from your reference table. So for the pendulum, you're doing a lab where you're going to see the influence of different factors on the pendulum system. So it turns out that the mass of the pendulum actually does not affect the period of the pendulum, but the length of the pendulum does affect the period of the pendulum, and the period is related to the square root of the length of the pendulum, and it's also related to the gravitational constant. So the period of the pendulum is inversely related to the gravitational constant. There's some practice problems that you'll do with those. We also want to think about energy and force at these different positions. So at the equilibrium position, we have the minimum force, but if we displace our object over to the left here, we are going to be in a position which I'll call A, where the restoring force is at its maximum. And the acceleration of this bob is at its maximum as well, because it's going from going to the left to stopping to turning around and going to the right. And in the middle here, it's just kind of speeding up maybe a little bit, or maybe not even speeding up in the instant before equilibrium and the instant after equilibrium. And then it starts to slow down and stop, and then we're at a place of maximum acceleration. So at these endpoints, which I'll call A and C, the restoring force is at its maximum, and the acceleration, and we would call this the angular acceleration because it's like along a curve, the acceleration is at its maximum, and the potential energy is at its maximum because it is the highest it will be above the surface of the Earth. And then the same for the mass on the spring, the potential energy is at its maximum at the endpoints because the spring is stretched or compressed at those times. So then if we think about the equilibrium position, the restoring force is at its minimum. For the pendulum, that restoring force is the component of gravity that's along that trajectory there, that red path. And there's no component of gravity in the equilibrium position that is along this path. So gravity caused it to go back to the equilibrium position. Then there's no net force along this path, but it's in motion, so it's going to stay in motion. As it swings back up, gravity is going to work to then bring it back towards equilibrium. So the acceleration is at its minimum here, and the kinetic energy and the velocity are at their maximum. And that's true as well with the mass on the spring. So it goes fastest through that middle point, and then it slows down and stops. Though it is going fastest through the middle point, its acceleration is actually the smallest because it's not actually getting faster, but it is the fastest. So for the mass on the spring, we have, again, that same idea. We're looking at a horizontal frictionless surface, the mass on the spring, and the midpoint is that equilibrium position, so I called that B. And then if we displace it a negative x amount, we're at the end point, which I think in the other one I called A, so we'll just call it A, and then in this one we'll call it C. So that negative x displacement is that endpoint A, and that positive x displacement is that endpoint C. And the restoring force, we'll recall, is the spring force, which is equal to the spring constant times the amount it changed its length, so delta x. And this negative just means it's a restoring force. It's trying to pull it back against the direction of the displacement. So if we displaced it in the positive direction, the force acts in the negative direction. If we displace it in the negative direction, then the force acts in the positive direction. So we'll see problems where we're looking at factors that change the period. So what happens to the period of a mass on a spring if I double the mass? So we'll use our comparison strategy like we went over with gravity. So we'll call the mass 2, we'll call the spring constant 1 because it hasn't changed, and then we'll call 2 pi 1 because that hasn't changed either. We'll choose our period of the pendulum equation, which of course we probably already did, and we'll substitute in these numbers that indicate the multiplicative factors that things have changed to get the multiplicative factor that the period would change. So it would be the square root of 2 times the original if I double the mass. So if my period was 2 to start, then my new period with double the mass would be 2 times the square root of 2. So the last thing I want to discuss with simple harmonic motion is position, velocity, and acceleration graphs. So if I displace my pendulum to the left here, then it would start with a position of negative x, or negative a, along this trajectory, this red trajectory. And this would apply to a spring as well. So at this endpoint, it would have a position of negative a, the amplitude. And for a pendulum, that would be theta. And then it would go to the equilibrium position. So that's a position of x equals 0 right in the middle here. And then it would swing over to C. So this midpoint is B, and then C, and then B, and then C. Then A, rather. And it would start over again. So we would get so this is a cosine graph, or a negative cosine graph. And then if we think about the velocity, so in your reference table, there's these two equations which show what the function of the position of an object in simple harmonic motion would look like with respect to time. So it would either be cosine or sine, depending on where you started looking at the object in simple harmonic motion. The velocity versus time graph would have a shape where at that end point, I'm actually stopped, and then I am, what happened here? And then I am getting faster. So we can see my position versus time is getting steeper, 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 steepest, and then it's getting smaller, 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 and then it's back to 0. So my velocity starts at the end point at 0, and then as it goes through the midpoint, it's the maximum, and then as it goes through the other endpoint, it's back to 0, and then as it goes through the midpoint again, it's at its maximum, and then as it goes back to the first endpoint, it's at 0. So I'd like you to draw this in your notes if you haven't already, and we'll look at the different endpoints. So we've got it started here, where it's at rest at the endpoint. It's moved through the equilibrium position, its maximum velocity, and then it's at the other endpoint at rest again, and then it's going the other direction. So we're going to go down. We can see our slope is turning negative here. It's the most negative it is at the midpoint. So just going in that opposite direction. And then it goes back to the other endpoint. So C, B, A. So we're like lining these up, if we can. So if we think about acceleration, well, acceleration is the rate of change of our velocity, right? So our acceleration is at its maximum at the endpoints, and we can see that the rate of change of this function here is steep and positive. So it's up here. And then the rate of change of the velocity through the midpoint is 0. So we're going to curve down to 0. And then it's going to reach its maximum negative acceleration because it's going to turn around and go the other direction. And then it's going to have a 0 acceleration as it goes through the midpoint. And then we'll go back to our left endpoint. So you can expect to need to construct these graphs and think about these things, and the activities that you're doing in class will help you do that. Hope this helps.